Before we start talking about this type of boundary area is why the plates move at all in the first place. And that's because of the hot material from the Earth's inner and outer core circulating, that hot, less dense material rising and being replaced by that cooler, more dense material. We call that a convection current. And you can see those in the picture right down here and right down here, causing the plates above them to move. So Earth's plates move because of that convection current. Just a quick review of that important idea for plate tectonics. Now, plate boundaries are where plates interact with one another, and there are many different ways that they can do that. The one that we're going to focus on today is called a divergent boundary. So think of a word like divide, splitting apart. A divergent boundary is a place where the plates are literally moving away from one another. Some real life examples here are the Mid-Atlantic Ridge, basically a line that runs down the entirety of the Atlantic Ocean, and it is splitting the Atlantic Ocean down that middle and increasing that seafloor both on the western and eastern coasts of their respective continents. Another place is known as the East African Rift, and that's in northeastern Africa, on the continent of northeastern Africa. And it is an area that at some point in the distant future that is going to be split off from the bulk of the African continent, and there will be a new landmass, and there will be probably part of the Indian Ocean that is going to fill in that gap at some point. So the idea of seafloor spreading is an idea that took many years to kind of develop, but it was first discovered by people mapping out the seafloor. So seafloor spreading is just an idea that says that hot mantle or hot molten material rises up and it erupts in these gaps or openings at divergent boundaries, and it pushes the existing seafloor to the sides, and as it does that, it causes that seafloor to spread apart or move in opposite directions at that divergent boundary. Before World War II, most people thought that the seafloor was pretty featureless, kind of like a large, flat, barren desert. And they really didn't have a whole lot of information to the contrary. Basically, the way that people used to map out the seafloor was by driving around, and they would drop a weighted rope down to the bottom. They'd take that measurement, and then they would drive another distance, drop that weighted rope again, and take that measurement. Obviously, by doing that in various points, you can see how a lot of detail could and oftentimes did get lost by using that kind of rope method to figure out what the seafloor looked like. So during World War II, actually in an effort to help with detecting things like submarines and map out the seafloor better, they used ships and a new type of technology related to radar called sonar, which is where you bounce sound waves out in multiple directions, and then based on what that sonar picks up, it can kind of tell you what the layout of, in this case, the seafloor really is. So it helped them map the seafloor in greater resolution, greater detail than had ever been done before. And that's one of the ideas that led to this discovery of these things called mid-ocean ridges and seafloor spreading, which eventually helped kind of modify that original continental drift idea into the plate tectonic theory that we subscribe to today. Another thing that when they found those mid-ocean ridges that they eventually figured out is that there are alternating magnetic stripes that are on either side of these mid-ocean ridges, and they determine that those magnetic stripes showed up that way because Earth's magnetic field, the north, what we call magnetic north and magnetic south, over time, over thousands and thousands and thousands of years, it switches. So you have the North Pole basically flip-flop with the South Pole, and the iron in these basalt ocean rocks on the seafloor will orient themselves based on the orientation of that magnetic field at the time that they formed. So we can not only see that the Earth has flip-flopped its magnetic poles over time, but we can also get an idea about how old these rocks are and also how often that magnetic field will switch. Some features that you find near seafloor spreading or divergent undersea boundary areas. You find these huge underwater mountain ranges that we call mid-ocean ridges, and these are areas at divergent boundaries where rock will form on either side of that divergent boundary. We can also track how often and how much the seafloor will spread based on the age of rocks. So you can have areas that are near the mid-ocean ridges that are made up of very young, relatively speaking, rocks, and then areas that are farther away from the mid-ocean ridges are much, much older types of rock. And one other kind of thing that happens not at the mid-ocean ridge or divergent boundary, but on the opposite side, because some people ask, well, if the ocean floor is spreading out here and increasing, wouldn't that mean that the Earth is always getting a little bit larger? And that would totally make sense. However, every time there is new ocean floor that is made, there is old ocean floor that gets consumed. And this is where we get into another boundary type related to convergent boundaries. But in these areas where that ocean floor is getting consumed, we call these deep water trenches, or just trenches for short, where two tectonic plates meet. The older, typically ocean plate, pushes under the newer, less dense plate, and we call this process subduction. But where that happens, opposite of where the seafloor is spreading at these mid-ocean ridges, that creates what's called an underwater trench.